All right. Yes, well, nap time now is, my poor wife is stuck with them. You guys can't hear, you sure you can't hear them? That'd be great if you can't. Okay, so the first thing I wanted to start off with, oh, that's good. Maybe I should give the lectures all the time on my laptop then. First thing I wanted to start off with is, if you look at our course syllabus, our next exam is scheduled for Thursday, the 12th. I might end up pushing that one day to the 17th. It just depends on how quickly we get through the topics. And these next couple topics can be a little difficult. So I thought we might benefit from one extra day of just application problems and studying and working on stuff, so that people do a little bit better on the next exam. Okay, but I'll let you know as we get closer to that. So just as a heads up, again, we may move it to the 17th. Most likely we will, but I'll know more next week. Okay. Did everybody enjoy the day off on Tuesday? Okay, that's good. And just as a reminder, we actually also have election day off, so that's good if you slept. So we also have election day off, so sounds like a trick question. No, it's okay. I enjoyed the day off, to be honest with you. I hope you guys did. I haven't, be honest with you, I haven't left my house really much since March, so my wife and I just got away a little bit, so it was nice. I'm not going to say who I'm voting for. That's inappropriate, but it is not the current president of the United States. Okay. Yeah, we went down to the Jersey Shore. I don't know if anyone's ever been down to the Jersey Shore. It's actually really nice. Got a little Airbnb, so that's where I am today. All right. I did not see Snooki. No. All right. So first off, even before we begin, I put a PowerPoint under course content. I put a PowerPoint here under week 8. I'm going to use it today. I want to start by letting you know that the first hour of class is a little difficult. Okay, so just bear with me. Like, I'm going to introduce a lot of definitions and some weird topics. And you guys ever know, like in mathematics, like or in some of your other classes, like a professor will put up definitions and it'll be like, wow, this is really weird. I don't really kind of understand what's going on. But then after they do an example or two, you're like, oh, okay, that kind of makes sense. Do people ever have that experience? Okay, because that's what this class is going to be like today, the first hour. Okay, bear with me. You know, like I've given this lecture, I don't know how many times over the course of my career, but I promise you that it's going to seem really weird at first, but then after you see an example, it's like, oh, okay, I kind of get it. All right. Everybody ready to jump right in? All right, good. I hope so. I've got my coffee ready, so. All right, so what is today's lecture about? Today is about what's called the uniform and normal probability distribution. So we're going to do a lot of probability questions, okay, today. So today's going to be about probability, but it's going to be very different than last section, okay? Like last section, I think, based on like the exam scores and stuff, I think last section was pretty tough, right? Like some of the probability questions are a little weird. Would you guys agree with that? Yeah, like, yeah, I think so. So what I like about this section here is there's going to be, and you'll notice as we go through the lecture, like there's a process to solving all the problems. Okay, like there's a step by step method, and the problems aren't as tricky. Okay, which is great. All right, and so we're going to learn about these things called over the next, finally. Yes, I'm sorry the last couple of weeks have been rough. You know, I get it. Probability is tough. But we're going to be learning about these things called probability distributions for the next 2.5, 3 weeks, okay? Okay, so what's the deal with this section here, okay? And forgive me if I seem a little slow. typing and stuff today. I'm just on a smaller laptop, so it's a little bit harder for me, okay? All right, so we're gonna do, oh, there's an echo on my end. How bad of an echo? All right, okay, but has the echo passed? You guys hearing me, not hearing me? No, you're okay? Barely? Oh no, how about now? Is this better? Not better, huh, guys? You can barely hear me? All right, now we're good? Okay, all right, so. Still good voice lecturing here? Okay, all right. Sorry about that. Oh, technology. Unfortunately, we're going to be remote again next semester too, so, you know, hopefully it gets a little bit better. All right, so let me know in the chat. I always have the chat open. Yeah, I have, yeah, we could, that's good. Some people love remote, some people don't. We can talk about it at the end of class if you want. We'll see how quickly we get through this section, okay? Antisocial, that's okay. All right. So in this section, we want to apply the concepts of a probability distribution to continuous random variables. Okay, so recall. Okay, so just recall. Last section was about discrete random variables. Okay, that's kind of where we ended class before we took the exam. So do you guys remember this? This was like, we showed probability distributions as tables. So what it kind of looked like, if you guys remember, it looked something like this. Does this ring a bell a little bit? I know it was like 10 days ago, but you know, okay, good. So now what we want to do is we want to apply this concept to continuous random variables. Okay, so if you remember discrete random variables, the deal with discrete random variables was they had a finite number of outcomes. Okay, have we heard the word continuous before in this class? I think so, right? Yep, way in the beginning, like, gosh, even 7 weeks ago feels like forever in today's world. Okay, so yeah, continuous random variables. What continuous random variables are, it means there's an infinite number of possible values. And these tended to be measurements of some type, okay? So here's where everything's going to be different, okay? So we're going to apply the concept of a probability distribution, okay, to these continuous random variables. And we're no longer going to use like these tables, okay? So instead, we're going to use curves. So the probability distribution will be shown with curves. Okay, and what I mean by that is with graphs, okay? How many people kind of remember graphing from, you know, maybe their other college level courses, right? Or maybe even high school, like graphing, you know, graphing functions or lines in mathematics. Okay. All right, good. We're gonna do quite a bit of curve sketching over the next 2.5 weeks, okay? And I think it's a lot of fun. All right, these problems actually. All right, everybody okay if I move on to the next slide? Yep, I can wait, no problem. And you guys will see as we go through these problems, it's just, I'm going to show you a step-by-step method to solve them. And you know, just bear with me as I get through the crazy definitions and everything. All right, Tora, are you okay if I move on? Yeah, no problem. You're more than welcome. Okay. So I have this example for today, and it's going to seem crazy, but this example is going to take us the first hour to get through. Okay. So we're gonna use it to introduce all the crazy definitions and stuff. So suppose that the United Parcel Service (UPS) is supposed to deliver to your a package to your front door, and the arrival time is sometime between 10 a.m. and 11 a.m. Okay, so let's just assume that they're gonna be right on time, okay, or they're gonna be in that window, okay. So the wait window is how many minutes? If they say they're going to be there between 10 and 11. Yeah, okay, thanks. 60-minute window. Okay, and let's just assume, obviously, that they're going to be okay. All right, that they're gonna definitely show up between 10 and 11. Okay. So do you know how long? Let me ask this. Do you know exactly what time they're going to show up at? Yeah, no, it's just like, oh, okay, they're going to show up sometime between 10 and 11. So, you know, that's an hour window, but you don't know the exact time. Okay. So we're going to define this variable. Okay. We're going to let the random variable X represent the time from 10 a.m. when delivery is supposed to take place. Okay. So what I'm really hinting at here is I'm going to let X be equal to the time spent waiting for your package. Okay. So now, is time a discrete or a continuous random variable? Was time discrete or continuous? Okay, yes, thanks, Leonardo. Yep. Okay, so time here is continuous. Okay, now let me give you some other information here. Okay, the delivery could be at 10 a.m. So if the delivery comes right at 10 a.m., can you guys see my mouse as well here? Just out of curiosity. Okay, great, awesome, thank you. So if the delivery comes at 10 a.m., okay, X is equal to 0. So you waited 0 minutes, okay, or it could come at 11 a.m., okay, which means X is equal to 60. So you spend 60 minutes waiting, okay, which is terrible because maybe it's like this package you really wanted, all right? So what we're going to say is with all 1 minute intervals of time between 0 and 60 equally likely, okay, what that means, okay, is your package is just as equally likely to arrive between 10:15 and 10:16 as it is between 10:40 and 10:41. Okay, so every minute is just equally likely to happen for your package to show up at. Okay, this right here, you'll see in a little bit. This right here is called uniform distribution, and that'll be made a little bit more sense in a little bit. Okay, what I mean by uniform distribution is like, oh, there's equal probability over intervals of the same width. Okay. All right, everybody got at least that, you know, that we're waiting for this package, and X is going to be the amount of time we spend waiting. That sound good so far? Okay, I got a couple of yays. Okay. So here's the question for the day, okay? And please do not overthink this, okay? what is the probability the package arrives sometime between 10 a.m. and 10:30? Okay. So this is going to be the probability package arrives between 10 and 10:30. Okay. I'm just curious. Does anybody know the answer? Don't overthink it. It's like it's, you know, don't even try to think of it as a math problem. Okay. Just like intuitively, can anybody tell me what the probability is that the package arrives between 10 and 10:30? Tora, that is exactly right. Do you want to turn your mic on maybe and tell us how you got that? Or you don't have to if you don't want to.
I mean, it's a half an hour time period and the entire time period is 1 hour, so.
Exactly, right? So that makes sense, right? So let me put this in terms of like the variable, okay? Do you want to say hi, babe? Come on, say hi to all my students. My beautiful wife is here.
Hi, everybody.
She walked in. She's, you know, this is supposed to be my time, but you know, she's walking in and.
I love you. I'm sorry. I just need my laptop.
That's cool. Just interrupt my work day.
No, I'm done. I'm done. I love you. Go learn. Go inspire the future.
Actually, my wife is a professor at Rutgers. She's a PhD. She's a brilliant. She's actually a survey researcher. So she does political polls, you know. Actually, I'll brag about her a little bit. She does TV appearances all the time because she's a pollster. She's been on CNBC, BBC. She's going to be on WNYC next week. So I married a rock star. Yeah. Yeah, it's cool. It's a lot of fun, actually. Oh, that's cool. I've never been on the national news. I am a lucky man. All right, so all right, let's get back to this, right? Okay, so written another way. Well, Leonardo, that's really, I'm gonna give you you're a good person for doing that. Okay, so to go back to this, just because we're in statistics class, we'll get back on target here. Written another way, if the package shows up at 10, you waited 0 minutes. Okay, if the package shows up at 10:30, you waited 30 minutes, okay? So what we're really looking at here is the probability that that random variable X, right here that I defined, the time spent waiting for your package, okay, is somewhere between 0 and 30 minutes, okay? And Tora walked us through why this answer is gonna be 1/2, okay? So keep this in your mind for the rest of class. Okay, because now I'm going to introduce a ton of crazy definitions, and I'm going to relate it all back to this example. So once I start giving the definitions and explaining how we're going to do this in statistics, just know that the answer, I'm going to re-ask this question, we're going to make it really hard, and the answer is going to be 1/2. All right, is everybody okay if I move on?
Yeah.
Okay. All right, so now we're going to begin with the definitions, okay? And these definitions are going to come up almost every day in class for the next 3 weeks. All right, so the first definition we have is what's called a density curve. Okay, and a density curve is a curve that represents the distribution of the continuous random variable. So a density curve, another way, is the visual representation of a probability distribution for a continuous random variable. Okay, so do you guys remember we showed for discrete random variables, we showed the probability distribution with the table. Now we're going to use a curve to show it, and we just call this curve a density curve. Okay, so whenever you hear me say the word, oh, density curve, okay, it's just the visual representation of the probability distribution. Okay. Now, again, I don't expect this to make sense until you see the first example, but just right now in your mind, okay, density curve, that's somehow related to a probability distribution. All right, is everybody okay if I move on from this? No more typing? Okay. Here's the next big definition. Okay, so this is the only other big definition from today. We have what's called a probability distribution function, and it's actually sometimes referred to as a probability density function. So sorry about that typo. I'm going to say probability density function for these things, okay? So a probability density function, PDF. Okay, so whenever I say the word PDF, am I far away now again? Am I good or not good? Not good, huh? Still not good? No good? I am not underwater. You got, so, yeah, just bear with the internet today. So I hear you. So what I'm also going to do, not only am I going to record this lecture for this class, it's, do I still sound like I'm in a fishbowl? So, okay. So what I'm going to do with this, I actually gave this same lecture in a different class, and the video quality is a little bit better. So I'm also, not only am I going to share the recording from this class, but I'll share the recording from the other class because it's a little bit cleaner. Okay. All right, so bear with me, and it just sounds like the audio is going to go in and out, but just try to stick with it. And I apologize. Next week will be better. Okay. So a probability density function is an equation used to compute probabilities of continuous random variables. So here's what we're going to be doing going forward. We're going to be computing probabilities of continuous random variables. Like if you look back here, I asked us a probability for a continuous random variable, okay? So we're going to use these equations somehow, okay, to answer these probabilities. All right, so it must satisfy the following two properties, okay? And if you satisfy these two properties, you're a PDF, you're a probability density function. So the total area under the graph of the equation over all possible values of this random variable must equal to 1, okay? So when you think of in probability, what does 1 represent in probability? Like what percentage is 1? Like if someone has a probability of 1, what percentage is that? Yeah, okay, good. Okay, so check this out. This is where it gets a little crazy, okay? The area, okay, under the graph is equal to 1. So what we're going to be doing here is we're going to be relating area to probability. Okay. The next thing that has to happen is the height of the graph of the equation must be greater than or equal to 0 for all possible values of the random variable. What this means is the graph never goes negative. Okay. So I should go back a little bit here. Has anyone ever heard the word function before in mathematics? Has anyone ever like, yeah, okay, so a few people have, and it's okay if you haven't. So what a function is you input values into this equation and it spits out something. Okay, it's a mathematical relationship. Okay, so what we're going to input into the function is some of our values of the random variable, and it's going to give us probabilities of something. Okay, and trust me, I get it. Like this definition, like what the heck is he talking about? It will make sense when we do the first example. So there's two definitions here now. We have this concept of a density curve and a probability density function. And the density curve is the graph of the probability density function. Okay, so a probability density function is an equation, and the density curve is the graph of this equation. Okay. Everybody okay if I move on? That's okay. I'll take a sip of my coffee while you're finishing. Tor. Yes, the PDF is the equation. Okay. Yep. Yep. And it'll make sense as soon as I do the first example. I promise. Okay. All right, Tori, are you okay if I move on? Okay. All right, so here is like the key concept of today. Okay, so if you're going to remember like one thing, just this slide is the most important. Okay, so how are we going to use these density curves in the probability density function? So the first thing you're going to do is you're going to be given a PDF, or you're going to find it. Okay, so you're going to be given a probability density function, and then you're going to sketch this density curve. Okay. Second, the area under the graph of the density function over an interval, okay, represents the probability of observing a value of the random variable in that interval. Okay, so like what the heck does that mean? Okay, that's like the key concept here. Area is going to be related to probability. Okay, so I want to find the area between two values of the random variable. So I'm going to go back for a second. Do you notice here, I have two values of the random variable. I have 0 and 30. Do you notice that for this example about the waiting for the package? So what I want to do is I want to find the area under the curve between 0 and 30. And that area should be 1/2. And that area is the probability of observing X between this 0 and 30. Okay. Okay, so here's the key concept, and this is going to be the key concept for the next like 2.5 weeks, okay? Area under the curve between two values is equal to the probability the random variable X falls between those two values, okay? So area is going to be equal to probability in this section. Okay. I know it seems a little weird, but we'll get there. Okay. All right, I'm going to move on. Is everybody okay? So I know I've been yapping for about half an hour now. So what we're going to do is we're going to now go into our first example, okay, where I hope that this makes sense. All right, so we're going to go back to this waiting for that package from UPS, okay? So the random variable X, so just recall we let X be equal to the time spent waiting for UPS package. Okay. All right, so the random variable X can be any value on the interval from 0 to 60. Okay, so that is that x could be anywhere between 0 is less than or equal to x, which is less than or equal to 60. Okay. Now this will help us in the coming slides. Think of this lower value, the first possible value of x, as the starting value. And think of 60, that last value, as the ending value. Okay, so it can only be between 0 and 60, right? Because I went on to say the two intervals of equal length between 0 and 60 inclusive are equally likely, then this random variable is said to follow what's called a uniform probability distribution. Okay, and so what we want to do in the next few slides is talk about what the heck is a uniform probability distribution. Okay, going back for a second, what is its density curve and what is its probability density function? Okay. All right, so now going forward, we're going to talk about this uniform probability distribution. Everybody okay if I move on? Not yet. Okay, no problem. Okay. All right, so some definitions, okay? What is the probability density function for a uniform distribution? Okay, so the PDF, the probability density function, we denote as f of x, okay, because it gets the function notation, okay? This is defined as what's called a piecewise defined function, okay? Has anybody ever heard of a piecewise defined function? Yeah, you would have, and it's okay if you forgot, but a piecewise defined function is something you would have covered in an algebra class. And what it is it's just a function that has different equations over different intervals. Okay. So piecewise defined function gets this function notation, or excuse me, this special bracket notation. And my apologies, that kind of looks like the side of somebody's face. Okay. But it's equal to two things. It's equal to 1 divided by b minus a for x between a and b, okay, and it's 0 otherwise. Okay, think of a and b, this right here, think of a as the starting value, and think of b as the ending value. Okay, have I used those words starting and ending value before? Yeah, I'm just going to quickly go back, right? Look right here. Starting value and ending value. Okay. So like my starting value here, A, is 0, and my ending value, B, is 60 in this example. Okay. So this equation is just super simple. It's just some function that's equal to 1 over b minus a whenever you're between a and b, and the function is 0 otherwise, okay? So now what is the density curve for this uniform distribution? Okay, so a density curve is the graph of this, okay? So we're gonna draw the first quadrant of the Cartesian plane. All right, along the horizontal axis, you get the values of x, which are your random variable. And along the vertical axis, you get this f of x function value. Okay, this function is equal to 1 divided by b minus a whenever you're between a and b, okay? So this is just going to be some number. So it's just literally going to be a horizontal line, just like that. Whoop, just like that. Sound effects and all, okay? And then whenever you're outside A and B, the graph is just equal to 0. That's it. So this graph here is literally just a horizontal line, okay? So, yep, and I promise you, actually, after you see the first example, once I do this with numbers, yeah, the answer, yes, always. Once you see this with numbers, it'll be like, oh my God, that makes so much sense. Okay, I promise you. All right. So just right now, I know it seems weird, but all the density curve is for this uniform distribution is a horizontal line. Whoop, that's it. Okay. So now what I'm going to do on the next few slides is take our example, okay, this waiting for the package, find the PDF and then sketch the density curve.
I just have a question.
Yeah, you can interrupt anytime.
So if it's only a line that goes like that in the middle, do we have to like graph it each time? Like, is there a point in graphing it?
Yes, well, because to answer your question, yes, because I'm going to ask you to graph like
But
on
it's
home.
like
homework.
that.
I'm sorry?
But it's always going to be like that, right?
Always. I've got 2 examples, okay? And you're going to see that in both examples, the graph always is going to look like this.
Okay.
Okay. All right. You guys ready to see the example now with numbers? Sound good? Okay. All right, so remember our random variable x, okay? So we're going to let x be equal to the time spent waiting for the package. Does anybody remember what the values of x could be? It had to be between what 2 numbers?
0 and 60.
Is my audio still out or is it okay now?
You sound so far away, like I can't hear anything.
So what we're gonna do, if you don't mind, when we go to take break in about 10 minutes, what I'm gonna do is I'm gonna cancel the class and then I'm gonna restart it. I'm just gonna try connecting to a different internet if that's okay. Does that sound okay with everybody? Okay. So not terrible or not terrible right now. Can you at least hear me get through this?
Can barely hear.
All right. You guys want me to try to just pause class now and come and try a different internet? Okay, let's try that. All right, so this will be our break and then we're going to come back to this, okay? It is 1:39. Let's come back at 1:45, okay? So I'm going to end the meeting, okay? And I'm going to try connecting to a different internet, okay? All right, I'll be back at 1:45, everybody, all right?